Hi everyone. So in this video we are going to talk about adding and subtracting fractions that have different denominators. Okay, so now to add and subtract fractions with different denominators, there's a few skills that you need to have. You need to be able to add or subtract fractions with the same denominator, because the technique we're going to use is we're going to take these fractions with different denominators. Let's look at the first example there, 1/3 minus 1/6, and change the denominators so that they're the same, and then go ahead and add or subtract using same denominators. So if you don't know how to do that, I have a video on same denominator fraction addition and subtraction. You also need to know how to find the lowest common multiple. Now for some questions like the purple one there, 1/3 minus 1/6, you might be able to get away without getting the LCM. Yeah, I mean you'll actually get the LCM, but you might not necessarily realize that that's what you're doing. But with other ones, like let's take the green one there, you probably need to calculate the LCM in order to get the denominators the same. To get LCMs, one popular method, one that I teach, is factor trees. So in order to get the LCM, you need to know factor trees or some equivalent method. And to do factor trees, it's handy to know divisibility rules. Okay, I have a video on each of these four, so go ahead and watch those if you want to. But these are the skills you need. So I'm going to start off with 1/3 minus 1/6. Now what I have to do is figure out how I can get an equivalent fraction for this 1/3 so that both have the exact same denominator. And in this case, if you know equivalent fractions, you know that you can multiply the numerator and denominator both by 2. And that if you do that, you'll get 2/6 minus 1/6. And then we have a fractions question with the same denominator. When the denominators are the same, you subtract the numerators. 2 minus 1 is 1. So the answer there is 1/6. Okay, so that's it. Pretty straightforward. Now, if you didn't know to multiply top and bottom by 2, numerator and denominator, you could actually use factor trees. Normally we wouldn't actually use them for a question like this, but we could. So let's go back and assume that we didn't know how to make these denominators the same. We would say, okay, well, I've got one denominator is a 3 and another denominator is a 6. Now the factor 3 for 3 is actually already done because it's prime. The factor tree for 6 is like this because 6 is the product of 2 times 3. So then we'd say, okay, 3 equals 3 and 6 equals 2 times 3. And to get the LCM, we want to put all the numbers here that are required to make a 3 or to make a 6 and not have any extras. Okay, well, to make a 3, we need a 3. That's pretty obvious. We don't need anything else to make a 3 because 3 is already prime. That's all you need. To make a 6, we need a 2 and a 3, so we add a 2 to our basket here. And the LCM then is 3 times 2, which is 6. All that's really telling us is that on our first step here, we want to have a denominator of 6 for both. That's what that's saying. And then we have to think, okay, well, what would we multiply 3 by to get to 6? Or in other words, what's 6 divided by 3? And the answer is 2. And so we would have to multiply the denominator by 2. But we don't want to change the value of this fraction. So if we're going to multiply the denominator by 2, we also need to multiply the numerator by 2. And there we have it. 2/6 is an equivalent fraction to 1/3. 2 minus 1 is 1. There we have it. Same answer. Okay, so that's the first one. Now this one's fairly simple in the sense that you can usually do it without the factor trees, without the LCM. You can just look at it and say, hey, if I multiply numerator and denominator by 2, my denominators will match. Let's move in now to the second one. 7/48 minus 5/84. It's unlikely that you're going to just be, oh, I know exactly what to multiply the numerator and denominator by. So here, we're going to use our factor trees, 48 and 84. And I'll just start factoring. I know 4 jumps out at me because 4 goes into 4 and 8. So I'm going to divide by 4. That gives me 12 over here. 4 is 2 times 2. 12 is 3 times 4. 4 is 2 times 2. So I factored 48 is 2 times 2 times 2 times 2 times 3. And 84, I'll do the same thing. Well, I see 4 again here. That's going to give me 21. 21 is 3 times 7. 4 is 2 times 2. So I know that 84 is 2 times 2 times 3 times 7. All right, good. So I'm going to write out that 48 equals 2 times 2 times 2 times 2 times 3. And I know that 84 equals 2 times 2 times 3 times 7. Those are the factor trees. Now, to get the LCM, I take a look at these prime factorizations. And once again, I have sort of a shopping cart. I talked about a metaphor in a previous video about least common multiple, where I've got two different dishes that I might want to make, a 48 and an 84. A 48 is made up of 4 2s, like 4 cans of corn, and 1 3, 1 onion, let's say. An 84 is made up of 2 cans of corn, 1 onion, and 1, I don't know, tomato paste, let's say, or beef. So what I need to do then is add to my shopping cart all the ingredients necessary to make either 48 or 84 without knowing in advance which one I want to make. So I'm going to look at the 2's first. I need 1, 2, 3, 4 cans of corn, because if when I get home my wife says, hey, I want a 48, I need to have this many 2's. If she says I want an 84, I'll just use 2 of the 4 cans that I bought. Okay, so getting 4 is enough to cover either dish without getting extra. That covers all of those, and that covers those. What else do I need? Well, I also need a 3. I need a 3 because if she asks for a 48, I need a 3, and if she asks for an 84, I need a 3. I don't need any more than 1 3. 1 3 is enough. Now, I already have enough here to make a 48, but if she asks me for an 84, then I also need a 7 as an ingredient. So I'm going to add that to my shopping cart as well. So then the LCM is 2 times 2 times 2 times 2 times 3 times 7. Okay, well, 2 times 2 times 2 times 2, that's 16, times 3 times 7, that's 21. So if I go 16 times 21, 1 times 6 is 6, 1 times 1 is 1. I put an X instead of a 0. You could put a 0 there just to show that I'm going over one place. 2 times 6 is 12. Put the 2, carry the 1. 2 times 1 is 2, plus 1 is 3. Then we add. I get 336. So that tells me that my LCM is 336, and in fact, that is going to be my denominator. Okay, like I say, unlikely that you just look at these two numbers and you'd say, oh, I know, it's going to be 336. You probably have to do this work here. By the way, I should point out here, there's a common method where you just multiply these two. That will always work. However, it's going to give you a lot more work to do than necessary. And when we get into some like these, or even more sophisticated ones, it could really turn into a mess. So you want to be able to get the LCM. Okay, just to show that, if I go 48 times 84, just to see how big that number is, let's see. 4 times 8, 32, 2, carry the 3, 16, that's 19, x, 8 times 8, 64, 4, carry the 6, that's 32, plus 6 is 38. Here we go, 2, 3, carry a 1, 9, 0, carry a 1, 4, okay? So we got 336, which is already a sizable number, but that's way better than working with a denominator of 4,032, okay? So getting that LCM really does help save us some work. So, all right, so we've got this. Now, I want to show you a neat little trick here, okay? So I'm going to actually take my shopping cart stuff, and I'm going to move it up a little higher so that you can see it right beside where we're working. And what I need to do now is I need to multiply numerator and denominator of this one by the number that would make the denominator 336. So I'm thinking, okay, 336 is 48 times what? Now, with no calculator, I'd be going 48, 336, and doing long division. And that works, but there's actually a simpler way. Look at this. 336 is this LCM, right? This equals 336. 48, I'm going to see which of these numbers are used to make 48. I can actually see it right up here. Maybe I'll get rid of these crosses that I made so we can see the numbers a little bit better. 48, whoops, I must have erased a, what was that here? 3, I believe. No, is that right? My brain is freezing. I'm feeling on the spot. Okay, no worries. I'm going to divide by 4. That gives me 12. Yeah, it's a 3. Okay, so we're all good. So now, look at this. 2 times 2 times 2 times 2 times 3 makes 48. 2 times 2 times 2 times 2 times 3 makes 48. And all you have to do is multiply by a 7 to then get to 336. So that tells me this 48 is already my 2 times 2 times 2 times 2 times 3. I just need to multiply by 7 in the numerator and denominator to get 336. So my numerator then will become 49. Okay, I could double check that. It's probably not a bad idea. 48 times 7, double check, I'm going to get a 336. 7 times 8, 56. 6 carry the 5. 7 times 4, 28 plus 5, 336. Bingo, just like I was expecting. Okay, let's do it again with the other one. This can really save you time, especially when you have no calculator. So I want to see what would I multiply the numerator and the denominator both by so that 84 becomes 336. Well, I'm going to look here, and I'm going to look here. 84 is 2 times 2 times 3 times 7. So sitting right here, I actually have 2 times 2 times 3 times 7. All I need to times this by to get to 336 is another 2 times 2, 4. So I'm going to multiply the numerator and denominator. Oh, maybe I'll do that in orange. I'm going to multiply the numerator and denominator both by 4. And I'm going to double check just because this is, supposing this is a new method to me. It's not a new one to me, but maybe it's a new one to you. I'm going to double check that this all worked out. Never a bad idea. 4 times 4, 16. 6 carry a 1. 4 times 8, 32 plus 1, 33. 336, right? As predicted. So there's actually some additional benefits to doing this LCM calculation in that you can actually use this prime factorization to your advantage to figure out what you're going to multiply numerator and denominator by on your fractions to get equivalent fractions with the desired denominator. All right, so far so good. Now, I've got a subtraction, the denominators are the same. So all I need to do here now is subtract the numerators. 49 minus 20, that's 29 over 336. All right, now at this stage, I'm not quite done. I have to see, can I reduce this? And this is one place where the divisibility rules come in really handy. If I factor 29, and if it has any of the factors that are here, then I can reduce. If 29 has none of these factors, I can't reduce. Okay, so these are the numbers I'm checking because 336 is composed of 2's, a 3, and a 7 all multiplied together. So if I cannot divide 29 by 2, 3, or 7, then I know there's no reducing that can happen. Now here you might look at it and say, hey, well, this is kind of obvious. 29 is prime, so clearly it can't be reduced, and I agree with you. But let's just, for the sake of argument, imagine we didn't know that and go through. So my factorability rules say, okay, 2. The only way for this to be factorable by a 2 is if the last digit is even, and it is not. Okay, so 2's out. 3. The only way for this to be factorable by 3 is if the sum of the digits is factorable by 3. The sum of the digits is 11. Is 11 factorable by 3? It is not. So that won't work either. 7 is tricky. It's actually faster just to do a division by 7 rather than try to use a divisibility rule. How many times does 7 go into 29? Well, 4 times gets you to 28, and then you're going to have a remainder of 1. So it's not divisible by 7 either. So therefore, this is reduced, and it is our final answer. Okay, 29, 336. Alrighty, last question here. Now, this is getting a little bit more advanced. Suppose here now we have a couple of fractions. They're actually called rational expressions. They get a new name once you start having algebra inside them, but the principles are all just the same. Suppose here now we want to add two rational expressions, fancy fractions, with x squared minus x as one denominator and x squared minus 1 as the other. Now, we need to factor both denominators, just like we did before in the other questions, right? I took 48 and 84. I found the prime factorizations using factor trees. Here, I showed you that you could do it also by factoring the 3 and the 6, although that was a pretty simple example where you didn't necessarily need to do it. Here, now, you wouldn't normally use factor trees, but you can. There are many ways to factor. I'm going to show you using factor trees just to make a connection here. And if you don't know how to factor these polynomials, that is probably okay if you're coming to this at a stage where you're just adding or subtracting fractions and say graded 8 or 9, for example. I wouldn't expect that you necessarily know how to factor these, but some of you might know, and so I want to show you. This factors into x times x minus 1. And this factors into x plus 1 times x minus 1. Now, if you don't understand why, don't worry about it, or go watch one of my videos on factoring polynomials. But if you know how to do this, look, this is the factorization. And so I want to get the LCM. Well, the LCM says we list the two and we write out the prime factorization. So this is the first denominator, the prime factorization, prime kind of in quotation marks, is x times x minus 1. These aren't really prime, but they're like primes because they can't be factored any further. X squared minus 1, that's x plus 1 times x minus 1. They're not actually prime, but they're like primes. Okay? And now for the LCM, I'm going to use exactly the same method as before. I'm going to pretend that I'm out shopping and I need to get all the ingredients so that I can make either that or that, depending on which one my wife tells me when I get home at the end of the day, but I'm not going to buy any extra ingredients. So I'm going to look at this. How many x's do I need? I need one x. How many x minus 1s do I need? I need one x minus 1. Okay, now I have all the ingredients to make the first dish. But look at this. I also need an x plus 1. So if I was asked to make this dish, I would have x minus 1 and x plus 1. If I was asked to make the first dish, I have x and x minus 1. Okay, these are all the ingredients. I have everything I need. So my LCM is actually x times x minus 1 times x plus 1. So that's what I'm going to do. And instead of multiplying it all together, like here I multiplied it all together and got 336, I'm going to leave it factored. It's just a little bit easier. So I have 2 as my numerator, x times x, what do we have here? Minus 1. Whoops. Okay. X minus 1 times x plus 1 plus 3 over x minus 1, x plus 1. All right. So now I need to think, what do I need to multiply the numerator and denominator by? And I need brackets. I've got to start being careful. What do I need to multiply the numerator and denominator by so that this one becomes this one here? Well, I'm going to look over here. X squared minus x is x times x minus 1. What is it missing to get to here? Well, it's just missing this part. So I'm going to multiply numerator and denominator by x plus 1. Watch. X plus 1. X plus 1. Okay. So here, actually, I shouldn't have a 2 by itself. I should actually have 2 times x plus 1. Here, I have an x squared minus 1, which is x plus 1 times x minus 1. What do I need to multiply the numerator and denominator both by here in order for this denominator to match this one here? Well, it already has x minus 1 and x plus 1. That's what multiplies together to make x squared minus 1. It's an x that is missing. So I'm going to multiply the numerator and denominator both by x, which means I actually have plus 3x there. Now, When I'm adding these fractions or rational expressions, the denominators match, so I just add the numerators. So my next line there is going to be 2 onto x plus 1 plus 3x over this entire denominator. Okay? And here there's a little simplification that we can do. I can use the distributive property here. Some people like to call that rainbow or fly fishing, other things, but it's the distributive property. So I go 2 times x is 2x plus 2 times 1 is 2 plus this plus here, I still have 3x over x onto x minus 1 onto x plus 1. And then I can collect like terms. So I have 2x, 2 groups of x, plus 3 groups of x, that's 5 groups of x total, plus 2 over x, x minus 1, x plus 1. Okay, and that's a fine answer right there. Some people might want to multiply this out and get a polynomial. You can do that too. Often you'd be happy just to leave it. And you also want to ask yourself, can you factor this, just like in the previous example here, can you factor this to reduce it? Is there a factor of x, x minus 1, or x plus 1 here so that we can reduce this fraction or this rational expression? And the answer here is no, and so this is the final answer.